Can you hear me? Can you hear me? Hello. My name is Paulo. I'm a student from University of Kent. I'm being advised by Dr. Dominique Archard. And I'm going to present my ongoing work on the metatheory of IRs and the CPS-calculus. Whenever trying to reason about functional programming languages, we always have a solid, strong foundation which we use for that. That's the lambda calculus. As shown by Plotkin, the lambda calculus can be used to define a functional programming language, and a functional programming language can be used to define the lambda calculus, because from the equational theory of the lambda calculus, we can derive a standard reduction sequence. So it doesn't matter how you reduct beta redexes, you can always reorder them from left to right, and a programming language will implement this reduction from left to right. On the other hand, the equational theory from the lambda calculus is sound with regard to the observational equality of the programming language. So one has a deep relation to the other. Because of this, we can always we can always use results established for the lambda calculus for reasoning about actual programming languages. So we have this strong foundation for programming languages. We can always resort to the lambda calculus, but we don't have such a common ground, such a core representation for compiler intermediate representations. So this was mostly exploratory work, and we are trying to fix this foundation and get something that can be used as a core for intermediate representation languages and study the properties they have. The lambda calculus is not a good idea for this because, as Plotkin showed on the same paper, beta reduction is too strong for terms in continuation passing style. So beta reductions reduce more than would reduce on source terms. So it's not complete for terms in CPS style. So we want to take a core calculus for intermediate representation that we can use results taken in those for reasoning inside compilers. We'll take TLX CPS-calculus and we start studying properties that haven't been studied about it before. So the CPS-calculus was introduced in order to study the categorical semantics of continuation passing, and it has a very simple syntax. We have basically two productions in here. So a CPS term is either a jump that acts as a function application to a function that can't return, or a bind that's a way of introducing intermediate values inside your computation. So in order to better understand this syntax, we can watch a translation from the CPS calculus to the lambda calculus that allows us to see that. For example, on a binding, K is bound on B, while X1 to Xn are bound in C. So for example, if we have this CPS term, this example are gonna be using through the presentation, it's actually equivalent to this lambda term. So we are just bounding these continuations inside terms, and we are doing some continuation applications in there. So just a church first introduced the lambda calculus as an equational theory instead of using directed rules that we use nowadays. The CPS calculus was introduced as an equational theory. So terms that are the same are based on 4 axioms. I can perform jumps to a continuation, so I can derive, this drives computation for me. I have extensionality, just as zeta reduction, the lambda calculus. I have garbage collection that says that I can introduce or remove continuations that are not being used. And I have a distribution rule that it is like the structural rules for the pi calculus that says, okay, I can reorder continuations. This can change the meaning of my program. Okay, but this doesn't tell us how to execute programs in CPS. So later, St. George and Mejo suggested a simple reduction rule that's a global rule deterministic, so every term has at most one redex that says we can take the leftmost jump to KE, and we can perform this jump without changing the bound continuations. For example, taking the same examples before, the leftmost jump is a jump to J. J binds a continuation to H. So we can exchange these, replacing the parameters. Now I have another redax because H is bound to a continuation to K. Now the leftmost position is a jump to K, but K is a free variable. So this term is in normal form, and I can't reduce anymore. Oh, this was actually based on actual the syntax for actual intermediate representations. So we can take the IR from Kenneth's paper here. This term is just the same term as an actual implementation for a compiler, just with different syntax. So binding is just a let, and perhaps in a more traditional notation, I can see an A and F on the right there. So these terms have the same meaning. Here, please don't worry about these rules. I added those just because I'm not a creative person. I didn't know how to illustrate this, but these rules are used as an efficient way of computing terms in CPS for compilers. These rules was taken for Kenneth's paper that in turn were based on APL's book. So this is how compilers implement the meaning of CPS terms, and I just moved this same relation to the CPS calculus because I want to explore what happens to it. So this is my first contribution. On the first paper by Plotkin again, he shows that the call by value lambda calculus, it is not as order restricted as it was first thought. I don't have to always reduce the leftmost redax. I can reduce any call by value beta redax in it because this doesn't change the observational meaning. So I'm first generalizing head reduction by saying, okay, I can perform jumps anywhere in the term, not only on the left. And I'm adding another rule that says, okay, if I'm not using a continuation, I can remove it because this can change the meaning. First, I thought this generalization was just an obvious idea. I thought I came up with those, but they actually are written in Kenneth's paper and in Appel's book. And these rules are just compiler optimization rules. They represent both functional aligning and that code elimination. And actually, these rules appear in the pi calculus as well, in the literature, and for explicit substitution calculus. So what's the main idea here? I'm using optimization rules as the operational semantics for the CPS calculus. We have more than one redax here. So now that we have more than one redax, we have to ask, is this confluent? Does the order of reduction matter? In fact, it doesn't matter. So I can perform functional aligning and that code elimination in any order, and I can every time join back the results. I can also factorize these steps. So whichever order I choose, I can always reorder those so that we can always start with the leftmost jump, just as we can in the lambda calculus. This means that inner steps can't be observed. So using compiler optimization rules as operational semantics is the conservative extension. It doesn't change the rules from using only a head reduction. Now we go back to the compiler rules, to the abstract machine semantics that's used for compilers. They actually coincide with head reduction as well. So by using this, I can reconstruct Plotkin's argument. Actual compiler IRs implement a prefix of the standard reduction sequence for the CPS calculus. And the equational theory for the CPS calculus is sound with regard to the operational equality on compiler intermediate representations. So the CPS calculus works as a foundation for intermediate representation languages. Okay, so far I have been talking about untyped terms, but what happens if we add a simple type system to it? In fact, by using a simple type here, the idea of types is always to derive a contradiction. So I have not t on one side and t on the other. I have a contradiction here, so this means this function can't return as expected from continuations. And this is actually normalizing. as a consequence, I can use the CPS-calculus, I can use a compiler intermediate representation as a logic system. In fact, this has been done before. There's a Curry-Howard correspondence for that because a subset of polarized linear logic can has the same rules as the simple type CPS-calculus. So this is a proof net that describes the cut elimination rules for simplifying rules in linear proof nets. And the cut elimination rules actually justify compiler optimization rules. So the same rules that are used for pi calculus for compiler optimizations also appear in linear logic. So to conclude my work in here, by doing this work that was mostly exploratory, I found close connections between several ideas in compilers, in logic itself, and in semantics of programming languages. I found out that using optimization rules is sound as an operational semantics for continuations. And we can have confluation, factorization, and strong normalization for that. All these results, I must mention, were formalized in Coq. I have 16,000 lines of Coq. This is on GitHub. Anyone can verify if you want. And the CPS-calculus indeed works as a foundation for IRs. So, for example, I can use the CPS-calculus to prove optimizations correct, and these proofs transfer to compiler representations. Finally, as future work, since the CPS-calculus seems to work as a logic, we want to explore dependent types in it. There are several results that say that dependent types don't work well with continuations, but our theory is that the reason for that is actually beta reduction, because beta reduction is too large for CPS terms. And we believe that using a notional reduction properly designed for CPS should probably fix the results and make dependent types work with continuations better. So that's it. Thank you very much.